Greetings everyone. In previous sections we discussed discrete random variables. And as you know, a random variable is considered a discrete random variable if it takes only a finite number of distinct values or countably infinite distinct values. Now we will discuss the other type of random variables which are called continuous random variables. A continuous random variable differs from discrete random variable in that it can take any value in an interval, which means it can take an uncountably infinite number of possible values. For example, random variables that measure something like temperature, height, distance, or time would be continuous random variables. Why? Because these random variables can take any values in some segment or even at the whole real line. In this section, we will talk about continuous random variables, probability density functions, and cumulative distribution functions. Let's start with number 1. For each of the following functions, find the constant c such that f of x is the PDF of a random variable x. A. F of x equals x to the power 3 divided by 4 for x lies between 0 and c. F of x is the PDF of our random variable x, which implies that the area under the entire curve must equal 1, which means the integral from negative infinity to infinity of f of x dx must equal 1. The integral of x to the power 3 divided by 4 dx has to equal 1. But we are not going to integrate this from negative infinity to infinity, because this is only the PDF between 0 and c. Outside of there, it's 0. So we are simply going to integrate this between 0 and c. So if we carry out this integration, we will get 1 over 4 times x to the power 4 divided by 4 evaluated at 0 and c. And so this is going to be equal to 1 over 4 times c to the power 4 divided by 4 minus 0 over 4, which equals c to the power 4 divided by 16. And we know that c to the power 4 divided by 16 must equal 1. So c to the power 4 equals 16. And this of course implies that c equals 2. F of x equals 4 x to the power c for x lies between 0 and 1. And we want to find the constant c. Again, since f of x represents the PDF of the random variable x, then the integral of 4 x to the power c dx from 0 to 1 has to equal 1. If we carry out this integration, we will get 4 times x to the power c plus 1 divided by c plus 1 evaluated at 0 and 1, which is equal to 4 times 1 over c plus 1 minus 0. And this must equal 1. So c plus 1 equals 4, which implies that c equals 3. Number 2. If x is a continuous random variable with PDF in this form, find the constant a. To find the constant a, we will use the property of any PDF, which is the integral from negative infinity to infinity of f of x dx must equal 1. Here, our PDF takes different forms for each interval. For example, f of x is defined as ax if x lies between 0 and 1, and defined as a if x lies between 1 and 2, and defined as negative ax plus 3a if x lies between 2 and 3, and defined as 0 otherwise, which means this PDF equals 0 if x less than 0 or x greater than 3. So the integral from negative infinity to infinity f of x dx will be equal to the integration from negative infinity to 0 of 0 dx plus the integration from 0 to 1 ax dx plus the integration from 1 to 2 of a dx plus the integration from 2 to 3 of negative ax plus 3a dx plus the integration from 3 to infinity 0 dx. The first integral is equal to 0. The second one equals a x squared over 2 evaluated at 0 and 1. The third one equals ax evaluated at 1 and 2. The fourth one can be divided into two integrals, which are the integration from 2 to 3 of negative ax dx plus the integration from 2 to 3a dx. And the last integral is equal to 0. After carrying out these integrals and added them, we will end up with 2a equals 1, which implies that a equals half. B. We want to find the probability that x takes on a value less than or equal to 0.5. We can find this probability using integration. First, note that the BDF is equal to 0 if x less than 0. So we are going to integrate x over 2 from 0 to 0.5. This is equal to half x squared over 2 evaluated at 0 and 0.5, which is equal to 1 over 16. Number C, find the probability that x greater than 1.5 and less than 2.5. Note that in case of continuous random variables, the probability that a random variable take any particular value is equal to 0. So, probability of x greater than 1.5 and less than 2.5 is equivalent to probability that x greater than or equal 1.5 and less than or equal 2.5. So here we will integrate f of x from 1.5 to 2.5. This integral will be divided into two integrals. The first one from 1.5 to 2 of half dx, and the second one is from 2 to 2.5 of negative x over 2 plus 3 over 2 dx. Why? Because f of x has different definitions on each interval. After doing these integrals and added them, we will end up with 0.4375. Number 3, if x is a continuous random variable with BDF given by k e to the power negative ax times 1 minus e to the power negative ax for x lies between 0 and infinity, and 0 otherwise. Find the constant k. Again, the integration of f of x from 0 to infinity is equal to 1. Since k is a constant, we can take it out of the integration. And the integration of the power function is 1 minus e to the power negative ax multiplied by its derivative is this power function to the power 2 divided by 2. هنا I multiplied the function e to the power negative ax times 1 minus e to the power negative ax by a علشان اخلي الفانكشن اللي جنب 1 minus e to the power negative ax هي الديريفاتيف بتاعها. وبالتالي الانتجريشن بتاع function multiplied by its derivative is this function to the power 2 divided by 2. Note that the derivative of 1 minus e to the power negative ax is 0 minus e to the power negative ax times negative a, which is equal to a e to the power negative ax. So the integration of a e to the power negative ax times 1 minus e to the power negative ax is k over a times 1 minus e to the power negative ax all squared divided by 2, evaluated at 0 and infinity. Note that e to the power negative infinity equals 0 and e to the power negative 0 equals 1. So this is going to be equal to k over 2a, which is equal 1, and this implies that k equals 2a. So our BDF is 2a e to the power negative ax times 1 minus e to the power negative ax for x lies between 0 and infinity and 0 otherwise. B. Find the cumulative distribution function. Remember that if a capital of x equals the probability of our random variable x less than or equal little x, and in case of continuous random variables, this CDF equals to the integral from negative infinity to little x of f of t dt. Note that introducing the variable t here because x is one of our limits of integration. So to avoid confusion between x and the variable x, we use t instead of x. So for x lies between negative infinity to 0, f capital of x will be equal to integration from negative infinity to x of 0 dt, which is equal to 0. For x lies between 0 and infinity, f capital of x will be equal to integration from negative infinity to x f of t dt, which is equal to integration from negative infinity to 0 of 0 dt plus integration from 0 to x to a e to the power negative at 1 minus e to the power negative at dt. The first integral equals 0, and the second one is equal to 2 times 1 minus e to the power negative at all squared divided by 2, evaluated at 0 and x. 2 will be cancelled with 2, and at the end the CDF equals 1 minus e to the power negative ax all squared. C. Find the probability that x greater than 1. This probability is equal to 1 minus probability of x less than or equal 1. And probability of x less than or equal 1 is just the CDF evaluated at 1. And this is simply going to be equal to 1 minus e to the power negative a all squared. So probability of x greater than 1 equals 1 minus 1 e to the power negative a all squared. Number 4. The length of time x needed by students in a particular course to complete in 1 hour exam is a random variable with BDF given by this form. Number 1. Find the CDF. Again, the CDF equals the integration from negative infinity to x f of t dt. So for x lies between negative infinity and 0, the CDF is equal to 0 since f of x equals 0 in this interval. And for x lies between 0 and 1, the CDF will be equal to the integration from negative infinity to x f of t dt, which equals the integration from negative infinity to 0 of 0 dt plus the integration from 0 to x 6 over 5 times t squared plus t dt, which equals 0 plus 6 over 5 t to the power 3 divided by 3 plus t squared over 2, evaluated at 0 and x. So the CDF will be equal to 6 over 5 x to the power 3 divided by 3 plus x squared over 2. And finally, for x greater than 1, the CDF will be equal to the integration from negative infinity to 0 of 0 dt plus the integration from 0 to 1 6 over 5 t squared plus t plus the integration from 1 to x of 0 dt. If we carry out this integration, we will find that it's equal to 1. Number 2. Graph the BDF and the CDF. The graph on the right represents the BDF of our random variable x. The horizontal axis represents the random variable x, and the vertical axis represents the BDF. If we draw this BDF by substituting different values of x in f of x, we will get this curve. Note that f of x is defined only on the interval 0 and 1. So before 0, f of x equals 0, and after 1, it's also 0. The graph on the left represents the CDF of our random variable x. This CDF is not a step function, as the case of discrete random variables. It's an increasing function starting from 0 and ending up at 1. Number 3. Use the CDF to find a probability of x less than or equal 0. This probability is a CDF evaluated at 0, which is equal to 6 over 5 times 0 over 3 plus 0 over 2, which is equal to 0. Number B. Probability of x less than or equal 1, also it's a CDF evaluated at 1, which is equal to 6 over 5 times 1 over 3 plus 1 over 2, which is equal to 1. Number C. Probability of x less than or equal 2 is a CDF evaluated at 2, but note that the CDF in the interval of x greater than 1 is equal to 1. Since 2 greater than 1, so f of 2 equals 1. Number 4. The probability that a randomly selected student will finish the exam in less than half an hour is probability of x less than 0.5, which is the CDF evaluated at 0.5, which is equal 6 over 5 times 0.5 to the power 3 divided by 3 plus 0.5 squared divided by 2, which is equal 1 over 5. Number 5. If x is a continuous random variable with BDF in this form, prove that f of x is a BDF. To prove that f of x is a BDF, two conditions must be satisfied. The first one is that f of x greater than or equal 0 for all values of x, which means the BDF can never take on negative values, and here x greater than 0, and our function is x e to the power negative half x squared. So this function takes only on positive values. And the second condition is that the integral over all domain of f of x dx must equal 1. So we need to prove that the integral from 0 to infinity of x e to the power negative half x squared dx is equal to 1. So the integration of the function e to the power negative half x squared multiplied by its derivative, which is negative x, will be equal to negative 1 multiplied by e to the power negative half x squared, evaluated at 0 and infinity. And this is equal to 1. So f of x represents a BDF. B. Find the first quartile and the median of x. The first quartile is the value of the variable that splits the data such that 25% of the values are less than this value and 75% of the values are greater than it. Let's call this value Q1. To find Q1, we need to find probability of x less than or equal Q1, which equals 0.25. Using the integration, this is equal to integration from 0 to Q1 x e to the power negative half x squared dx, which equals 0.25. This integral will be equal to negative e to the power negative half x squared, evaluated at 0 and Q1, which equals negative e to the power negative half Q1 squared minus e to the power 0, equals 0.25. Note that e to the power 0 equals 1. So this is equal to e to the power negative half Q1 squared, which equals 0.75. Take ln for both sides. We will find that Q1 squared equals negative 2 ln 0.75, which equals 0.5754, and finally Q1 will be equal to the positive square root of 0.5754, which equals 0.7585. Note that we take the positive value of the square root, not its negative value, since x greater than 0. So the first quartile will be positive value. To find the median, we will do the same steps of the first quartile, but here probability of x less than or equal Q2 equals 0.5, where Q2 is the median. Number 6. Let the distribution function of a random variable y be in this form, and we want to get its BDF. All we need to do here is to differentiate this CDF to get the BDF. First of all, we will differentiate the first value of the CDF, which is 0, and its differentiation is also 0. Then we will differentiate y over 8, and that gives us 1 over 8. And then we will differentiate y squared over 16, which is equal to y over 8. And finally, we will differentiate 1, which is equal to 0. Now, we can write down the BDF as 1 over 8 when y lies between 0 and 2, and y over 8 if y lies between 2 and 4 and 0 otherwise. B. Find the probability of y lies between 1 and 3. This probability can be obtained using the CDF as the CDF evaluated at the upper bound minus the CDF evaluated at the lower bound, which means f capital of 3 minus f capital of 1. The CDF of 3 will be equal to 3 squared divided by 16. And the CDF evaluated at 1 will be equal to 1 over 8. So 3 squared divided by 16 minus 1 over 8 equals 0.4375. C. Find the probabilities that y greater than or equal 1.5, which equals 1 minus probability of y less than or equal 1.5. And probability of y less than or equal 1.5 is a CDF evaluated at 1.5. So probability of y greater than or equal 1.5 equals 1 minus the CDF at 1.5, which equals 1 minus 1.5 over 8. So 1 minus 1.5 over 8 will be equal to 0.8125. D. Find the probabilities that y greater than or equal 1 given y less than or equal 3. This is equal to the intersection between y greater than or equal 1 and y less than or equal 3 divided by y greater than or equal 3. The intersection between probability of y greater than or equal 1 and y less than or equal 3 is y greater than or equal 1 and less than or equal 3. And we already get this probability, which is equal to 0.4375. And the probability of y less than or equal 3 will be the CDF evaluated at 3. So at the end, the conditional probability is going to be 0.778. Number 7. If a random variable y has a BDF of the form b over y squared for y greater than or equal b, show that this BDF has the properties of a density function. As we said before, to prove that f of y is a BDF, we need to prove that our two conditions are satisfied. The first condition is that f of y greater than or equal 0 for all values of y. Here, since b is the minimum time, so it's positive. So b over y squared is always positive for all values of y greater than or equal b. The second condition is that the integral over all domain of f of x dx is equal to 1. As you can see, the integral from b to infinity of b over y squared dy is equal to negative b over y, evaluated at b and infinity, which equals negative b over infinity minus b over b, which equals 1. Note that minus b over infinity equals 0. B. Find the CDF of y. So, for y less than b, the CDF will be equal to the integration from negative infinity to y of 0 dt, which is equal to 0. And for y greater than or equal b, f capital of y will be equal to the integration from negative infinity to y f of t dt, which is equal to the integration from negative infinity to b of 0 dy, plus the integration from b to y of b over t squared dt. The first integral is 0, and the second one أكنه b times t to the power negative 2. So its integration is b times t to the power negative 1 divided by negative 1, which is equal to negative b over t, evaluated at y and b. So the CDF for y greater than or equal b will be equal to 1 minus b over y. C. Find probability of y greater than b plus c for a positive constant c. Probability of y greater than b plus c equals 1 minus probability of y less than or equal b plus c, where probability of y less than or equal b plus c is the CDF evaluated at b plus c. So probability of y less than or equal b plus c will be equal to 1 minus b over b plus c. So probability of y greater than b plus c equals 1 minus 1 plus b over b plus c. Cancel 1 and negative 1, then this probability will be equal to b over b plus c. D if C and D are both positive constants, such that D greater than C. Find probability of Y greater than B plus D given Y greater than B plus C. This conditional probability is equal to the intersection between Y greater than B plus D and Y greater than B plus C divided by probability of Y greater than B plus C. Note that D greater than C, then B plus D greater than B plus C, which means Y greater than B plus D contains Y greater than B plus C. So, the intersection between Y greater than B plus D and Y greater than B plus C will be Y greater than B plus D. Again, since Y greater than B plus D contains Y greater than B plus C, so the intersection between them is Y greater than B plus D. If we use the CDF to get these probabilities as the previous question, we will find that this conditional probability is equal to B plus C divided by B plus D.